Hi, welcome back. In this lecture, I want to focus on one-qubit quantum gates. I will start first describing what is a quantum gate and which kind of matrix formulation can express quantum gates, and then I will focus on introducing to you a class of quantum gates called one-qubit because they act on a single qubit. But let's give a start. So a qubit is a two-level quantum system, and its evolution follows the laws of quantum mechanics. In particular, it follows this Schrödinger equation if our system is isolated from its environment. So if we take a quantum system that does not interact with the environment, then it obeys to the Schrödinger equation that we have in this slide here. So let's look at closer this equation. From one side, we have a so-called operator that is called Hamiltonian that is related to the energy of the system. This is an operator, so therefore introduce the transformation on which quantity? Well, the quantity for which we write this equation is the state vector, psi. So we use our bracket notation, and then psi is a general quantum state. So an operator acting on a quantum state is equal to the change in time of the state vector itself multiplied by I, which is the imaginary number, and then h bar, that is the reduced Planck constant. Luckily enough, we don't need to go to the physics detail. We don't need to solve the Schrödinger equation to understanding the transformation of a quantum gate on a state. We don't need to know how to solve a Schrödinger equation. What we're going to do, we're going to express a transformation on a quantum state as a matrix vector multiplication. So these metrics represent a linear transformation and will be our quantum gates, and it will act on a state vector, our ket psi. So let's go in this direction. So as whenever we use a quantum circuit model, we are working in a finite dimensional space. That is our qubit that will have two components, and each component will be so-called amplitude. And we're going to have a fixed basis. For instance, we saw in the previous lecture, we have the computational basis. The operation and transformation in quantum circuit formulation are described by matrices that express a linear transformation on our quantum state. And this operation will be applied to vectors that represent our qubit state. According to the quantum mechanics, not all the matrices are valid quantum transformation. Only the matrices that are unitary can represent a transformation in the quantum computing and quantum circuit. So what is the definition of a unitary transformation? Well, a unitary transformation is a linear transformation that is invertible, so it can be reversed, and also it preserves the norm. The formal definition is the following. If we take U, that is our unitary transformation, and we'll multiply by its adjoint, this is equal to the identity matrix. Inverted operation is just U adjoint. So let's see why unitary transformation are important. Well, as I said, the major first characteristic is that the unitary transformation are reversible, so we can go back and forth. So whenever we apply unitary transformation on a qubit, we get resulting qubit, we can go back to the original qubit configuration, but just apply its adjoint, that is its inverse. The other very important properties of the unitary matrices is that they preserve vector lengths. So if we have a vector, in this case it is psi, we apply our unitary transformation and obtain U applied to psi. The vector that is resulting from this transformation has the same norm, so has the same length. So unitary transformations are quite popular in computer graphics. So many of the computer graphics transformations are unitary because they preserve the norm. For instance, rotation of vectors are unitary. We're going to focus on one-qubit gates in this lecture. So these will be unitary transformation that are going to be sized 2 times 2 because the state vector of a qubit is of dimension of 2. The simplest example of a quantum gate is the identity matrix that is represented here. So we have 1 on the diagonal, and we can represent as was a 1 box. So here we have our qubit that is going to be a vector with the 2 amplitude, and then we apply the identity matrix to obtain the very same vector that we gave as input. Let's go and see something less trivial. This is the X gate that you probably know as the NOT gate. So the NOT gate is represented by this rectangle with the X, or you can also find sometimes a NOT, and is expressed by this matrix you see here on these slides. So why is called NOT? Well, if we apply this matrix to the ket 0 that is represented by this column vector, so this is multiplied by 0, this is by 0 multiplied by 1, 1 by 0, so the first element is 0. Then if you take the second row and multiply by the column, we get 1 plus 0 multiplied by 0, so is 1. So you see that we go from state vector 0 to state vector 1. And obviously the same happens. Let's say that we apply to state 1 this transformation. You can do the matrix vector multiplication and we obtain the state 0. So it's just flipping. In general, let's say that we have a general qubit state in a superposition. What the NOT gate does is just to flip the amplitude of the state vector. Something that is very peculiar to quantum computing and quantum circuit formulation is the so-called H gate, also Hadamard gate. And this some gate that has no classical analog. So this is very, very important. The Hadamard gate has this matrix formulation, you see. And what is doing? Well, the Hadamard gate is our door to quantum superposition. It can create superposition of state. So if we apply the H gate on a qubit in state 0, this is classical state, we can give as an input. The resulting state vector is equal superposition of state 0 and 1. If we apply the Hadamard gate to state 1, we obtain again a superposition, but look at here, we have a difference in the sign. To summarize, the Hadamard gate allows us to go from a classical state or classical bit to a superposition of state. It acts in a different way. Either in the case of acting on state 0, we get the plus sign here, and this quantum state, because it's kind of peculiar, get the name of ket plus. When we apply it to the state 1, we have a change of a sign here, and this state is also called ket minus. Let's look at another important gate that is called the Z gate. By combining the previous Hadamard gate and the NOT X gate, we can obtain the Z gate. So we apply first Hadamard, NOT, and again Hadamard in a sequence. This also corresponded to multiply matrix by matrices, the single matrix formulation of these three gates. So what it does is quite interesting. So if we have initial state that is in state 0, it will end up again in state 0. If the initial state is 1, again it will be in state 1, but with the change of phase here. Matrix formulation can be expressed using this matrix here that can be obtained by multiplying the matrix formulation of these three gates. Since there are X and Z gates, there is also be a Y gate. And why so? Well, these represent some sort of rotation along three different axes, X, Y, and Z. That's why I'm saying that we could expect that. So the matrix formulation of the Y gate is on these slides here. Pauli matrices take the name from Wolfgang Pauli, one of the father of quantum computing. The set of identity matrices X, Y, and Z are known as a set of Pauli matrices and are quite important in quantum computing. One of its main attractive properties is that the Pauli matrices constitute a basis of a vector space of 2 times 2 complex matrices. So this is a set of matrices that represent a basis for all the quantum circuit transformation. Together with X, Y, Z, Hadamard gate, other important matrices that is quite common to encounter in quantum computer are the S and T matrices that you can find on this slide here. Their transformation is acting only on the second amplitude of the qubit. It corresponds to a rotation of pi over 2 and a rotation of pi over 4. In the next lecture, I will introduce a geometrical representation of a single qubit state known under the name of a block sphere, and we will explain how all one-qubit quantum gates can be understood as a certain kind of rotation in the block sphere. This is the last slides of this lecture. Talk to you soon.